introduction, part 1. We'll cover the structure of the module and Bayes' theorem again, that this is all machine learning is based on. So structure of the module, from her website. You can also buy physical copies if you want to. You will also be given and directives and other papers and things throughout this module that you will also have to read. Okay. Instructions. We need to cover these 4 things for this session. The pattern recognition / machine learning cycle, features, objects, dataset, labels and classes, supervised and unsupervised machine learning, and Bayesian probability models. You should all be familiar with these things already, but this is a recap. Okay. So the pattern recognition machine learning cycle. Now that I've put my teeth back in, we start off with the real world, where all the problems come from, what we're trying to actually solve in the real world. We want to predict something, we want to work out how something works, we want to find patterns in something. Then we have to collect features and the data that we're going to use within these algorithms. We need the actual data underlying to work it out. Then we need to decide if we're going to go down the unsupervised or the supervised route. What dictates whether we can do unsupervised or supervised? Whether or not we have a ground truth. So whether or not we have a correct answer to refer back to. Most often, that will be in the form of class labels. Sometimes they're in terms of cluster labels. Sometimes they're in terms of an actual value we should be predicting. But we need to have a ground truth, an actual real answer that we can check our model against. If we have that, which version do we do? Supervised, thank you. If we don't have the ground truth, we have to do unsupervised. So if we are going to do unsupervised, we first have to select a clustering method. Now, there are no fixed hard and fast rules on how we select a clustering method. As much as machine learning is a science, there is an awful lot of experience that comes into it. Things like, oh, I've seen a data set like this before. This method happened to work very well last time. We will try this first. There's no guarantee that that method will work fine this time, but it's a good starting point. Then if it doesn't work, we try another one, and we try another one, and we try another one. There is no set of rules. There is no website, paper, or anything that I can point you at that says, if your data is this, use that. Or if your problem is that, use this algorithm. There is an awful lot of trial and error involved. Once we've got a method, we then cluster the data, and then we have to decide if the result is okay. Now, how do we do that? Because we don't have a ground truth. That's why we're doing unsupervised learning. How do we decide if the result is okay? Sorry, so setting up the model with the ground truth. So we haven't got that either. The model. I don't think so. The result seems reasonable. If your clustering has put together, and you're trying to detect different animals, for example, and it's put giraffes with lions, is that reasonable? No. If it's put giraffes with other giraffes, and maybe different types of dogs and a pig together, okay, they are similar. It's not completely correct, but it's reasonable overall. So we can't actually have a terribly good empirical measure to say this result is good, this result is bad. We don't have a ground truth. We can't absolutely for 100% say this is right, this is wrong. We as humans can make a judgment of if it's reasonable or not. Ordinarily, we as data scientists would do that first and say, well, to us it looks reasonable. Then we'd give it back to our user and say, we think this is okay, what do you think? They might turn around and say, no, it's absolute rubbish, go back and do it again. But it's left down to a judgment rather than a measure. So if a result is not okay, we have to go back and do it again, or go back and pick a different method. Because sometimes we just reach the limit of a certain algorithm and it's not going to work differently. If the result is okay, we return it to the real world and it gets used. Perfectly reasonable. Now, if we are doing supervised, we have a slightly different process. We select and extract the features that we're going to use, because sometimes having more data actually adds confusion. It adds difficulty where it wasn't there before. So not always is more data better. Having more data to use if we want to is better, but our model may not use all of it. So we may have to select. Other times, we may have to engineer or extract new features using things like PCA or TSNE or any one of 100 other algorithms to create synthetic features based on our data. What comes next? Anyone? After we've got our features? We need to select a classifier. Absolutely. What comes next now? We've got our features. We've picked which classifier we're going to use. What happens next? We need to train and test the classifier. It's only afterwards that we'd end up with confusion matrices or any metrics, but we have to train and test. We may use any one of the different protocols you've studied. Which ones have we studied? Cross-validation. Type of cross-validation, isn't it? Sorry? Leave one out. There's one more. That's the shuffle. Data shuffle is the other one you missed. So we could use any one of those protocols. Why do we do the different protocols? Why wouldn't we just use resubstitution all the time? To avoid overfitting, yes, to avoid generating a classifier that recognizes specific data only and doesn't generalize well. So once we've done that, we then come to determining whether the result is okay. This time we've got metrics. We've got a ground truth so we can calculate exactly how good it is. What sort of metrics would we use? Accuracy is one. F1. Sensitivity. Recall. And what's the other one? Precision. Yes. And which ones go into the F1 measure? Precision and recall. Yes. So what happens if the result is not okay? Well, we go back to any one of the 3 prior steps. Maybe we picked out the wrong features, and that's what's thrown it off. Maybe we need to use a different classifier because the classifier we've picked isn't suitable for the type of data we've got. Or maybe we simply have to change the training and testing protocol and we try again. The last step is that when we've got a result that does work, then we return it to the real world again and it gets used to solve the actual problems. Okay? So let's recap some of the definitions. Features, objects, classes, and data sets. So when we're talking about features, we denote that with the Latin x, that's the squiggly x, and 1 up into lowercase n, which is our number of features we've got total. An object we represent with a bold letter, and it represents a value, a set, which is why we use the square brackets, of every single one of those features. And it's transposed because we've turned it into a row rather than a column. Where it exists, that's what the curved E means, in Rn. So that's the values of the real numbers in an n-dimensional space. Does that mean that Rn, the n in Rn, is different from the xn? No, it's the same in both. So if you've got 4 features, you are talking about an object in 4 dimensions. You must have a value in each one of those features, therefore it is the same thing. So when we're talking about dimensions of data, or dimensionality, or dimensional space, we can think features. The feature exists in those dimensions. Sometimes data scientists do use the word feature and dimension interchangeably. Okay? A data set is labeled with a capital letter, usually Z, and it contains all of the objects from lowercase of the same letter 1 to lowercase of the same letter capital N. So lowercase n is the number of features or dimensions. Capital N is the number of objects in our data set. And every single one of those has to exist in the same real n-dimensional space. Yep. Labels are similarly a list. Why is it a list? We're using square brackets and a set. Anyone know the mathematical difference between the two? Got to be all of them, isn't it? In the labels, the order matters. Yeah. So we have to make sure that we've got the list of labels in a certain order, and it has to match the same order as the data set. Yeah. In sets, you cannot have duplicates, and the order doesn't matter. In a list, the curly brackets, you can have duplicates, and the order does matter. So, for example, if you reordered your data set and you didn't reorder your labels the same way, what's going to happen? You're going to be labeling the objects wrong, aren't you? You're going to be attaching the wrong name badge to all of you. Yep. If I laid out name badges for everybody on your desks before you got here, and you didn't pay attention, the order does matter. Okay? And each label has to exist within omega. That's the Greek symbol that looks like the horseshoe. Okay? And that represents the list of classes, or the set of classes. So every label given to an object has to exist within the set of classes we've got. We will use numbers like 1, 2, 3, 4, or 0, 1, 2 if you're doing it in Python. However, classes can have names. They can have an actual real name. We could have a class of Ernest, for example. He'd be pretty lonely on his own, because there's only one Ernest in the room. But we could use names as classes. We could call things Triangle, or we could call things Miami if we wanted to. It doesn't have to be numbers. However, we will be using numbers in this course. Okay, so let's make sure that we can understand and differentiate these concepts. Now, how many objects do we have in these pictures? Absolutely right. How many classes have we got? 2. Absolutely right. The whole thing is the data set Z, every objects we've got. We've got two classes, one red fox and one fennec. Okay, good. So when we're looking at what these things look like, we're talking about supervised learning because we've got the class labels at the end. Our data set is the whole lot, but we recognize this in terms of tables. We've got rows that represent a single object, and we've got features that represent a single column. An actual value is where those two things intersect. So that is the value of feature 2 for object 3, which happens to be the value 2. When we have supervised learning, we have an extra bit that is the class labels. Now, when we're talking about it in programming, those can either be a separate array, like it's shown there, a completely separate bit on its own, or you might find that the dataset has been provided with the class labels as being the final column of the data. Which is why, on Monday, the first thing we did in question 1 was split them up, so that we weren't confusing the class labels as a piece of data. Okay? But it doesn't always have to be that they arrive all in one portion. So, learning how to assign a correct class to an object is the same thing as training a classifier. Now, if I told you to work out how to distinguish animals, you'd be learning how to tell them apart, wouldn't you? If I say it's got webbed feet, a bill, and wings, what is it probably going to be? Well, it's not going to be any bird if it's webbed feet. It'll be something like a duck or a seagull, yes. It's going to be a water bird, certainly. How would we then learn to tell ducks and seagulls apart? We'd need more features, wouldn't we? If we say that it's black and white, webbed feet, bill and wings, it's probably going to be a seagull. If it's brown, it's probably going to be a duck. Those rules, very simple rules by human standards, are a classifier. Learning how those rules work is how we train a classifier. So, I've highlighted or pointed at object number 395, which is that blue circle on the right hand side in the middle. And it is assigned class label blue circle. How would we work out how to tell that blue circle apart from all the other data? Well, we wouldn't know the color and the shape because that's just how I plotted it on this data in terms of x1 and x2. We don't know that x1 and x2 represents color, or it could be the nearest things it's closest to are also other blue circles. That would be a nearest neighbor type classifier. It could be that we could draw two lines to try and split them up, and that would be a linear discriminant classifier, or technically two for two lines. What else could we do? We could do rule-based and try and divvy up the space into smaller and smaller sections. Yeah. What else? A decision tree, which is again an extension of rule-based, isn't it? What other things could we do? We could use the more advanced classifiers like support vector machines and translate this into a higher dimensional space where they can be nicely split up. We could use XGB, yep. All of these are just different algorithms, aren't they? Fundamentally, we still have to teach each one of them about that data set. We still have to teach them where all the different points are, or a majority of the different points are, to avoid overtraining. to work out where the class labels and the classification regions are. Yes? Okay, so we do the same thing again, but this time for unsupervised learning. The data doesn't change. It's still, each row is an object, each column is a feature, but this time we don't have the extra portion that is our class labels. We don't have that ground truth. So we have to work out some kind of structure that makes sense. For example, we could do something like this to try and find a structure in that data. Now, do we know if that final answer is right? No, we can't tell if it's actually correct or not. It just might seem reasonable. Now, if we were to classify that ourselves, what would we think? Would we think 5, or would we think there's less? I don't know about you, but I think that there's possibly, to start with, something like a class there, another class there, and a class there. That's sort of what it looks like to me. Which one's right? We don't know. What I think is reasonable might not be the same as what the end user thinks is reasonable or you think is reasonable. Okay? We don't know if one is better than the other. We have nothing to compare it to. Okay? Right. So, that's recapping all the terminology, the process, and how we do supervised and unsupervised learning. So let's move on to the Bayes probability model. Probability, mathematically, is all about measuring the chance of something happening. If something can never possibly happen at all, ever, anywhere, it's just not possible, then the probability of that happening is 0. If it is guaranteed to happen every single time, no matter what, the probability is 1. For example, is the probability of Peace turning up to a lecture impossible? Well, she's sitting there. It's happened, so it can't be 0. Is the probability of Peace turning up to a lecture guaranteed to always happen? She is shaking her head that she hasn't gone to. The probability can't be 1. Is the probability that when a lecture goes on that I'm going to be here 0, 1, or something in between? If the lecture goes ahead, I'm usually going to be the one that gives it, so therefore the lecturer being present is going to be 1. Everything else is somewhere in between. It's only when it can never possibly happen ever for any reason, or it is absolutely guaranteed no matter what, that we absolutely know what the values are. We can calculate the rest based on the data we know. The first thing that we can use is the prior probability. So when we have the class labels, we can measure the probability of each class happening based on how many we've got. The sum of all of the probabilities that this object is one of the classes must, by definition, add up to 1. It has to be one of the classes. Okay, it's not going to be none of them. It has to be labeled somehow. So how do we then work out the rest? Well, first thing we have to look at is conditional probability. Need to put my teeth back in. Probability density functions. So we're saying here that the likelihood of sampling getting the value x out of the class Wi is going to be something. I has to be 1 up to the number of classes that we've got. Then we have the posterior probability. So this is the chance that the true class of the object is the one we picked. What are we saying with the posterior probability? What measure are we actually using here? It's not just accuracy. It's a accuracy of something. So I can't hear you when you talk at once. It's true. That's the same thing as just the accuracy. And accuracy of the prior probability. The prior probability cannot be wrong. It cannot be inaccurate because it's calculated. It's not something we guess. What we're saying is that it's the accuracy of each class. The posterior probability, if we say the posterior probability of finding X in that population, we're basically saying we're getting that population right 60% of the time. Not the whole problem, not the whole classifier, which is what we tend to think of when we say accuracy with no other clarifying remarks, but for that one class. And that means that just like the prior probabilities, the posterior probabilities for all classes must also add up to 1. Yep. Let's take an example that I used with my previous semester module, but I'm sure we have a disease. Let's say it's COVID. Okay? And it affects 99% of the population. If I was just going by accuracy, my classifier would just say not infected. Yep. And therefore, it would be right 99% of the time. That sounds really good, doesn't it? 99% accuracy, we'd take that. But because it doesn't do anything smart, it misses entirely the infected class. That one person that has got COVID, it doesn't find. So, what are the prior probabilities of this system? Well, 99 people won't have it, and 1 person will. So the possibility of not being infected is 99 out of 100. The possibility of being infected is 1 out of 100. We add those two together, we get 100 out of 100, which is the same thing as 1. So we've proven the prior probabilities add up to 1. Let's take the posterior probability of my classifier that does nothing but say not infected. How many of the 99 not infected people will it get right? 99. So 99 out of 99 it gets right. How many of the infected does it get right? 0 out of 1. We add those two together. 0 divided by 1 is 0. 99 divided by 99 is 1. We've proven the posterior probabilities add up to 1. Okay? The ideal, so the ideal classifier, which doesn't exist in the real world, is the Bayes classifier. It should always assign the class label corresponding to the largest posterior probability. The chances that we're actually going to get that population right more of the time. This way, the error for every object will be the smallest possible that we can. What's the problem? Well, we don't know the posterior probabilities for every single object that might be in the data set. We can work it out for the ones we've got, but that's not the guarantee for the things we haven't seen yet. Yep. I can work out the probability of people passing this module from are in the room or have done the assignment. But what about the people that didn't come to the lecture or didn't do the assignment? Can I tell whether they were going to fail or not? Well, 10 years worth of experience as an educator tells me if you don't turn up to class and you don't hand in work, you're pretty much going to fail. Yeah. However, some people are just smart enough to be able to pull it off in an exam or whatever else to pass. So I cannot guarantee that I know the answer. I think I do. I'm guessing with a probability that I'm right, but I can't guarantee it. So, the chance that X is actually WI is incredibly difficult to estimate. It's incredibly difficult to work out. But it is related to saying, is this thing likely to be in that class in the first place? Through the famous Bayes Theorem, which is shown on screen. So the probability that WI contains X is worked out as the probability of it being WI in the first place, and X is going to be in that class, divided by the probability of all of the other ones. Which is also the same thing rearranged as the probability of it being that class, times the probability of that thing being in that class, divided by the probability of it being that thing. Now, how do we go and work this out? Well, we can estimate those sorts of things. We can estimate those two values. And then we work out the rest. So, for example, in one dimension, we've got a data set here, this x-axis. We've got two classes. We've got black dots and we've got red crosses. At any given point, the probability of it being one of those two things are shown by these lines. So up until this point here, it is more likely to be a black dot, isn't it? Well, we can tell that because if we extend this line down here, we can see on the left-hand side there are far more black dots than there are red crosses. Great. That proves that point. On the other side, there are far more red crosses than there are black dots. So the probability says that anything less than 1 is probably going to be a black dot, sorry. Anything bigger than 1 is probably going to be a red cross. So, let's just extend that a bit further. If we do the actual maths, that's what happens. So at this point, it's not quite 1. It's a little bit over 1. Anything less than that the posterior probability, the chances that we're right of calling it a black dot, is highest. So we call it a black dot. Same thing happens with the bigger than. So let's consider a new problem. Why did this decide not to move on? Right, so to show you it works, let's consider an example with one categorical feature. What do I mean by categorical? It's going to be a fixed set of values, isn't it? It's going to be one of a set thing. It's not going to be 1.7459999. It's going to be one of a certain set. That feature that we're going to call X, and we can observe, is color. So one of these objects can be one of the colors and nothing else. It has three possible values. So it can only be either red, blue, or green. That's our data set. That's our Z. Class 1 has got a load of circles. 4 of them are red, 2 of them are blue, 2 of them are green. Class 2 has 3 red triangles, 2 blue triangles, and 6 green triangles. So what do we have in this data? Suppose this is the whole population. So this is not just a sample. This is all the data there could always ever possibly be. Class 1 with 8 objects, 4 red, 2 blue, 2 green. Great. Class 2, 12 objects, 3 red, 3 blue, 6 green. If we draw an object and observe that the feature is blue, which class label should we assign? Well, according to Bayes' theorem, let's work it out. We can estimate these bits, okay, but actually we can calculate the rest of it because we have all of the data. There's no other data possible in the world. So let's work out the prior probability of each class. So class 1 has got 8 objects in it of whatever feature out of 8 plus 12, the total number of objects we've got. So 8 out of 20, which means that the prior probability of it being class 1 is 0.4. The prior probability of class 2 is 12 out of 20. The same 8 plus 12 on the bottom, because that's the total numbers, and there's 12 in class 2. So the prior probability of it being class 2 is 0.6. Everyone with me so far? Okay. So now, class conditional, so the class conditional, so which class it's in, probability, and we're saying that it's a probability mass function because it's a categorical, it's not density, it's mass because there's only set values. So for class 1, if X is blue, then we're saying that the chances of it being blue in class 1 are 2 out of 8, or 0.25. In class 2, the chances of it being blue is 3 out of 12. Okay? Once we've got that, we can calculate the posterior probabilities using the theorem. So let's recap what we've got here. So we've got the prior probabilities and we've got the conditional probabilities. So let's figure this out. So the probability that X is blue is the sum of all the different classes of the probabilities here. So when I fill it out, the probability of it being class 1 is 0.4. multiplied by the probability of it being blue within that class. So 4 times 0.25. Plus, for the second class, the probability of it being in class 2, that's our 0.6, times by the probability of it being blue in class 2. 0.6 times 0.25. So the posterior probability of X being blue is 0.25. So we've worked out that bit. So for class 1, we can take the probability of it being class 1 times the probability of it being blue in class 1 over the probability of it being blue at all. 0.4 times 0.25 divided by 0.25, giving us 0.4. Class 2, we get the same thing. Probability of it being class 2 times by the probability of it being blue in class 2 divided by the probability of it being blue at all. 0.6 times 0.25 divided by 0.25 gives us 0.6. Okay? So, 0.6 is bigger than 0.4. So the Bayes classifier, the one that uses the largest prior probability, says if we draw an object that's blue, we should call it a triangle, class 2. Because it's more likely to be, based on our data set, a triangle when it's blue. Plus, we've also proven again, 0.6 plus 0.4 equals 1. The posterior probability added up to 1. So we see the colour, and we know out of the 5 blues, we have a 3 in 5 chance to have drawn a triangle, and a 2 in 5 chance of drawing a circle. If we always label blue objects in triangles, we will make a mistake in 40% of cases. No other strategy, no other way of making that decision based solely on colour will give us a better result. That is the best possible error we could get, or best possible accuracy. This is why we say that the Bayes classifier is optimal, or has optimality. It does the best it possibly can based on the statistics we put in. Okay? So, a question. Try and reproduce the Bayes classifier example for the following population containing 3 classes. We can only tell by colour. Distinguishable by colour. We can only, though, measure the shape. So this time we're not using the colour as the distinguishing feature, we're using the shape. So I want to know, what is the class label if we draw a triangle? What is the class label if we draw a circle? And what is the class label if we draw a diamond? And prove to me what the reason is that the Bayes classifier makes the optimal solution using only one of the values of X. Okay? Now I'm going to give you some time before we move on to the next part. We work out all the numbers, or if you need to go to the loo or whatever, that's absolutely fine. We will start again at